Hi everybody. So this is a quick revision lesson for level 3 waves on linear motion only from mechanics, and we are starting off first of all with momentum. And I don't know why the screen's becoming like that. Okay. So this is a revision lesson with quick brief notes for linear motion, which you can finish looking at in about 5 minutes. So we start off with momentum, and momentum is to do with motion. The unit is kilogram meters per second. Just remember that momentum is a vector, and so direction is important. And looking at change in momentum caused by an unbalanced force, and you can have a change in momentum if either the speed, direction, or mass changes. There are two possible formulae to calculate change in momentum, which is final momentum minus initial, or force multiplied by time as change in momentum. The only thing you have to keep in mind is that you have to flip the direction of the initial momentum by 180 degrees because you're subtracting vectors. If you're given a force versus time graph, you can also get the area under that force time graph to get the change in momentum. And then the other thing is impulse is another term for change in momentum. Conservation of momentum, whenever you don't have external forces, then in collisions and explosions, the total momentum before collision equals the total momentum after collision. Then this brings us to the center of mass, which is a point on an object where that object will balance if it's pivoted. When you're looking at the center of mass of a system, it could be one object or multiple objects. Let's consider two objects. There are two ways of calculating it. One is using the idea of torques. So this little triangle here is the pivot point, and so mass times distance from the pivot on one side equals mass times distance from the pivot on the other side. The other way of calculating center of mass is by using a reference point, and using a reference point is you have something like a bank and which doesn't move, so there's your bank. And if there's water and a plank floating on water and there's somebody on the plank, the person moves, the plank is going to move. So to find the center of mass of the system, all distances are taken from the reference point. Okay, now let's move on to the next one. The velocity. So there are two things to do with center of mass. One is finding the position of the center of mass. The other one is finding the velocity of the center of mass. So this is used by looking at conservation of momentum. So when there's no external force, the momentum of the system is conserved, and the momentum of the system is total mass times the velocity of the center of mass, which is actually made up of the momentum of the individual masses that make up the system. And so you have this formula over here, so this one there, which has to do with momentum. Okay, that is the velocity of the center of momentum. And what your center of mass, what you need to know that because momentum is conserved, the center of mass will move in a straight line at constant speed if it is moving, or if it's not moving, it's going to be stationary. Then let's move on to circular motion. So it's caused by this unbalanced force, your centripetal force, which is always directed towards the center of the circle. What the centripetal force does is not to change the speed, but to change the direction of motion. So what we need to remember is that the speed is given at a tangent to the circle at any point, so the direction of the velocity is changing the whole time. Centripetal force acts 90 degrees to that. And also when you have an unbalanced force, you have your acceleration, which is your centripetal acceleration. Here's your formula for centripetal acceleration, and because unbalanced force is F equals ma, then you have the formula for your centripetal force. Now, what provides a centripetal force could be friction, gravity, or tension, depending on what it is. And if you're not given the velocity, you need to use v is equal to 2 pi r over t to find the speed. That was mostly level 2. In level 3, you've got banked curves and conical pendulum. So the conical pendulum is like a simple pendulum, but it goes around in a circle. So what we need to do is the unbalanced force is actually, the forces acting is tension force on the string and gravity force downwards, and we actually resolve the tension force into the horizontal and vertical components, and the vertical component of the tension force actually balances the gravity force. Bad mistake, I had the rubber and I rubbed that off. Okay, here we go, gravity force. And the horizontal component of the tension force provides centripetal force. So you have the Fc, which is actually mv squared over r, is Ft sine theta. Now, moving on to banked curves, you can adapt the same sort of rule to banked curves. So in order to do greater speeds, the sides of the roads are often raised up at the edges. This is called banking. And greater the angle of banking, the faster speeds. So what we're doing here, again, very similar. We are resolving the reaction force, which acts at 90 degrees to the surface, into vertical and horizontal components. So your Fg, which is mg, is equal to the vertical component of the reaction force, and your horizontal component is your unbalanced force that provides centripetal force. Now there's an easy formula to do this. You combine this and you get this v squared equals rg tan theta to do your calculation. So you don't have to do all these steps. It saves you lots of time in an exam. And moving on to gravitation, so any object that has mass has a gravitational field around it, and this is represented by field lines, and the arrows point towards the object, okay, inwards. And the gravitational field strength is how strong is the gravitational field at some distance away from the mass or on the surface of the mass, and that's given by gm by d squared, or r squared, could be either. And where g is a universal gravitational constant, and that's 6.67 times 10 to the power of negative 11 Newton meter squared per kilogram squared. Now, gravitational force is the force exerted by any object on another object, so it's proportional to the product of the masses and inversely proportional to the square of the distance between them. So just be careful, the distance is what we see in this diagram over here. So if you're just given the radius of the Earth or something and the height of a satellite above the Earth, you've got to do the radius plus the height in order to get that distance. Bringing us to satellite motion, assuming it goes in a circle around a planet, you have the centripetal force provided by gravity force, and in order to get the speed with which it goes, you just equate these two and you get square root gm over r, which tells us the speed of the satellite doesn't depend on the mass of the satellite, but just on the radius of orbit. And let's move on to the next one, vertical circular motion. So you've got horizontal as well as vertical. So in order to go in a circle, you need a centripetal force. What's important is the forces at the bottom of the circle and the top of the circle. So at the bottom of the circle, you've got the reaction force acting in an opposite direction to gravity force. So you need to subtract the two to get your resultant centripetal force, which is directed towards the center. And at the top, you've got to add them because they're both in the same direction. Now, just moving on to the feeling of weight depends on the size of the reaction force. So bigger the reaction force, the heavier you feel. So it's at the bottom of the circle that you feel heavier. Okay. Now, in order to keep water in a bucket which is being revolved or spun around in a vertical circle, this will happen if you have some minimum speed, because if you stop or go slowly, the water is going to fall down and you're going to get very wet. So for the minimum speed, that's when your reaction force reduces to 0. So your centripetal force is provided by gravity force. You equate the two and you get V is equal to square root Rg, or V squared equals Rg. Now, looking at energy conservation in a vertical circular motion, so I've just given an example of looping the loop, which is there on your roller coaster rides. So you have the higher hill, which is the capital H, so that's the height of that. And all the energy at the top is gravitational potential, which is mg capital H. When it comes down to the bottom of the loop here, all that gravitational potential energy is converted to kinetic, provided no energy is lost in the form of heat because of friction. But when it rises to the top of this little curve, over here, the top of the hill, which is not as high as the original hill. It's moving as well as it's at a height, so it's got two forms of energy, gravitation potential as well as kinetic. And so I just equated the energy at the top here to the energy at the top of this lower hill. So, and that's why I end up, the relationship between capital H, the height of the high hill, and the radius is H is 2.5 R. Okay, and so that brings us to the end of linear motion, and I hope that was useful.